before I call upon the first speaker, I have a couple of announcements. First thing is that people might have noticed that tomorrow morning's first talk is shown as 8:40 in the program, but that's a small mistake. The actual sessions will start at 8:30 as usual. Kindly note down, we'll start at 8:30 tomorrow morning. Secondly, regarding the list of participants, I've been told that the list will be ready by tomorrow morning and all the delegates will be getting a copy. With these two, I now request the first speaker for this afternoon, Dr. Kasagi, and we will follow yesterday's pattern of requesting the speakers to introduce themselves and also the affiliation of the laboratory. Dr. Kasagi.
Yeah, we started at what? Seems to me this training session is sometimes a contest how first we can speak in English. In that sense, our Japanese has a great disadvantage, so you should put a handicap for us. But anyway, I have no time to speak. So my title of the poster is something like this: Anomalous enhanced DPT reaction in paraffin oxide. We observed this very recently. So I just stated quickly how we did the experiment and what kind of result we got. And of course, our purpose is the nuclear effect can be affected very strongly by the environment. In that sense, we started to measure the TD reactions in metal at very low energies, let's say down to 2 keV. And the purpose of why we study is if nuclear reaction occur really at room temperature, the reaction rate should be tremendously enhanced. In that sense, we might observe the enhanced reaction rate even at higher energies. Then the question is that DD reaction in metal really enhanced or not? If there is enhancement, in what kind of metal and how much enhancement? So far, we studied the titanium and yttrium, and we reported this result at the in this conference at Toya, Hokkaido. And we continued this program since then, but present data we got very recently because of some interruption of a program of machine. What we have made in our laboratory is this kind of so-called low energy high intensity beam generator, and deuteron beam is organized here by the geoplasmatron ion source and extracted something around 20 kilovolts and go through. But here we have a decelerate electrode, and then you can get a very low energy deuteron beam. What we really measure is just not a real cross section, but a thick target, so-called thick target yield. Our target is so thick to the beam energy, then the deuteron is energy of the deuteron is decreasing in this material. So what we are observing is just this integrated yield of the reaction up to the incident energy. So what I showed you here is the previous result. For example, this is for titanium. And you see the energy scale is from 2 keV to something around several keV. And this is the so-called thick target yield, which is normalized to the 10 keV, at the 10 keV. And then this dotted line is just the prediction from the ordinary cross sections. And in this case, almost no enhancement. So this is the standard. We can say, actually, this is a little bit enhancement here, around here, but let's say there's only a 10 or 20% enhancement. Now, I'll show you the very recent result. We are very lucky to do the experiment with Russian physicist. Here's an audience here, Dr. Dixon. He brought us this kind of material, PDO, PD, AE, gold. And you see, this is the same yield, fixed target yield for this target, and the red point is the result. And blue line is again the reaction fixed target yield without enhancement. And you see we also did a palladium measurement here, which I showed here with an orange square box here. So you can see the tremendous enhancement around here. This is like about 50 times enhancement without enhancement. And what I plotted here is just a prediction with the so-called screening potential. I have to say this screening potential is in center of mass energy. So in that sense, this is a laboratory energy. In that sense, the reaction is almost enhanced by 1.2 kV. So I think it's very significant because of, I have to stop, just one. So if the cross-section can be extrapolated with the screening potential parameter, as I showed you, the 600 electron volt for PDO and 250 electron volt for PD, then if we can extrapolate it to the room temperature, then the estimated cross-section is something around this range, 10 to minus 49 to 10 to minus 40 square centimeter. And that brings this rate. That's it. Thank you.
Thank you very much. Dr. Chelandi, Richard, understand you speak on the results of his trial to the Cincinnati group experiment.
Okay, this is a very preliminary result about the measurement we make in the Cincinnati cells about transmutation. We get the Cincinnati cell as a present at the end of November, and we can start after some levels of the custom and safety only in February. This experiment was made at CICCF. This is the oldest, most prestigious nuclear laboratory in Italy. They have a very good quality instrumentation, so the results, I think, are of good quality. So they have at the same time a lot of nuclear physics and chemistry. And they make for a long time studies in uranium, thorium, and plutonium. So they are not beginners. We made a total of 4 experiments, 2 black experiments and 2 black experiments. The black experiment was made mainly to understand how the system works. Before starting the experiment, I asked that the cells be mechanically cleaned. There was the possibility of some brain contamination and acid etching and so on. Anyway, we test with 7 and max 8 no stench material on the surface, except thorium, zirconium and acid. So we start the experiment using sodium nitride instead of thorium in order to understand how the system works. And we start with the same procedure of Cincinnati group, so means from 50 volts. But after a short time, the pressure increased so much that the safety valve break, so we have to stop experiment. The second experiment, we use only 1 drop of protein acid as people recommend, but we use a different approach. So we start from very low voltage, 10 volts, and we increase voltage until the current naturally decreases. This time this experiment can be done successfully. At the end, we clean again the cell well and we carry it clean again. The first black experiment, we used following the protocol of number 2, and we used thorium, but it was not only thorium natural, thorium 232, but the thorium at 230. The density of 230 was 1210 natural thorium. We make experiment and okay, we have the fourth experiment using a procedure is the compromise between our procedure of 50 years and Cincinnati protocol. So it means starting from 10 volts, but we have a large current. And we make a chemical analysis and the total radiometric alpha plus beta analysis. The results are the following. You make a strong announcement. So using only ICP mass spectroscopy, we detect a lot of mass. But when you match with ECP optical, about 90% of what you detect disappears. So I think it's mandatory to use both techniques to be sure about results. Anyway, even under this strong constraint, you get something. Moreover, we recommend don't use glass for collect all the liquid and solid, but only Teflon. Because basically just to use fluoric acid so the glass can leak boron, silicon, and other elements. So in the black experiment, we detect almost nothing strange. In the black experiment, the result was more or less similar. And we get boron, cesium, mercury, and copper, and a lot of other elements. We have to still analyze from the point of view of quantitative. Okay. So the chemical deficit was about 80% for test experiment number 3, and the radiometric about 12%. So the number 4, 22% chemical and 14 for total chemical, total radioactivity. The boron detected was natural, 3.2 milligram, large amount. Kappa between 1 and 1.5 milligram, not natural spot ratio. Cesium 133 and mercury. Other elements are still under analysis. Okay. According to our the results used the so-called Cincinnati cell is able to transmute not only natural thorium but even at 230. The amount of food materials in our laboratory 50S or 60 is less than 10 from Cincinnati group, but even of miserable amount. We just cross-checking the result with this mass in the optical and need some more food study. Thank you.
Thank you very much, Mr. Next speaker is Dr. Mizuno from the Hokkaido University. Dr. Mizuno.
I would like to show you my recent result, namely measurement of the transmutation on several metals by strong Cathodic electrolysis. I have continued to detect the transmutation element on the electrode after electrolysis. However, it needs long-time electrolysis. I have found a technique that gives us very easy transmutation elements. Here, I use the platinum electrode, and I use light and heavy water solution. Here, I use such as alkaline solutions. Alkaline solutions. These are very high purity reagents. This is a schematic drawing of my experiment system. Basically, the electrolysis cell is a very conventional type. It is made by quartz, 5 centimeter diameter and 15 centimeter height. Temperature was measured by Teflon coated thermocouple at 3 points. Heater was used for calibration. All the data, temperature, input voltage, and current were accumulated in floppy diskette through a data logger. Here, I have designed to measure neutron count and energy spectrum by helium-3 and Me213 scintillators. This shows the electric light emission of the sample plate of platinum in sodium carbonate light water solution. This color changes by alkaline ions and electrolysis conditions. Maybe you have known in this morning session by Dr. Omori's lecture. These photographs show typical result of platinum electrode surface observed by scanning electron microscope before discharge, and this is after discharge. Before discharge is very flat and uniform, but after discharge, the surface was completely changed. The surface seems once melted. After the discharge, you can see many elements were deposited. This is a typical result of EDX measurement. You can see large iron, copper, nickel, chromium, potassium, and calcium peaks, alkaline carbonate materials. However, each experiment, I can see such kind of element. The distribution and intrinsic elements were changed by electrolysis conditions. Thank you.
Thank you very much, Dr. Thompson. Next speaker is Dr. Iyazi. He is from the same group as Dr. Botha.
My name is Felice Iazzi, representing the Torino group, whose activity since the beginning of the cold fusion was dedicated to the search for nuclear ashes. And since a few years, we have concentrated our efforts in detecting the helium-4 in the plastic glass going through helium plus energy reaction, trying to overload the palladium sheet by applying an electric field at the ends of this sheet, the so-called Thorium effect. The palladium system looks like here, and these are the two electrodes. The atmosphere around the sheet is of deuterium, of course. the results concerning the helium excess was positive in 2 cases over 4 and were presented in the previous perfusion conferences. And starting from the 97, we have tried to look at the correlation between helium excess and several parameters like temperature of the PD system, the atomic ratio D over PD, and the intensity of the applied electric field. Also, we are developing a diffusion model to look in some detail at the local concentration of the deuterium inside the matrix. A part of this program has been fulfilled concerning the correlation between the atomic ratio, local temperature, and electric field. I just show you the kind of electric field that we have applied. 3 electric fields, different in intensity, shapes, and what we have learned from this measurement is that we succeed to obtain high concentration of deuterium inside the matrix when we applied a high intensity current, but with not too steep shape of the current. In this case, the concentration alpha goes down because the current is steeply increasing. In this case, the second case, in the third case, sorry, concentration alpha reaches a high value of about 0.8 because the current is smoothly increasing in the time, during the time. The second result that we have obtained is the correlation, strong correlation between the high concentration obtained and the measurement of the temperature in the center of the sheet and near the cathode. In the case of the field 2, where we didn't reach high concentration, we have always observed a temperature near the cathode lower than in the center of the sheet. While when the concentration reaches the highest values, we always observed a higher value of the temperature near the cathode than in the center of the sheet. And this surely indicates that the deuterium ions migrate toward the cathode and they accumulate there. For more detail and for discussion, I will write before you at the panel. Thank you.
Our next speaker is Dr. Chai. He's a colleague of Dr. Takahashi from Osaka University.
My name is Qiao. I belong to Osaka University, Japan. My title is Measurement of High Energetic Particles from Titanium Sheets Implanted with Deuteron Beam. To look for the signature of a coherent multi-body fusion, we have carried out the experiments of deuteron beam implantation using a highly parallel TIDX target and a counter telescope of delta E and E, charged particle spectrometer. As a result of experiments, helium-3 4.75 MeV and the same energy tritium from 3D fusion proposed by new class of fusion theory in solid were repeatedly observed. we identified two unique charged particles as products of the reaction channel of 3D. By the combinational analysis of the one-dimensional and two-dimensional data, experimentally obtained 3D fusion rate was in the order of 10 to 3, that were surprisingly large value and was enhanced about 10 to the 26 times compared with the traditional theory of DD reaction. This figure shows a schematic drawing of the experimental apparatus. We have used a highly pure DIDX plate sample, and the sample was mounted on the pellet device for the cool. On the beam running, beam current was about 30 microampere, and the temperature of the sample was about from 5 to 15 centigrade. We have used the charged particle spectroscopy with silicon delta E and E detector. Also, we have used a simple silicon detector called the EK detector. Of course, we set up aluminum foils in front of these detectors to reject scattered neutron. This figure shows a charged particle spectra from DIDX plate and neutron beam stimulation, where P2 and T2 denote proton and neutron by normal D diffusion. As you can see, we had two strange shoulders, here and here, and a high energetic peak, this. Especially, we identified these shoulders as products of the reaction channel of 3D fusion. In detail, I will discuss about the result of the experiment at the poster session room. Thank you.
Thank you. Next speaker is listed as Dr. Matoya, but since she just arrived, she will be coming at the end of all the papers at about 3 o'clock. The speaker after that is Dr. DeNinno from Kasagi.
We did a study on material science, which main goal is to improve the reproducibility of heat excess experiment. We have studied the influence of microstructure on PD samples, and we did a systematics in order to understand which is the mechanism that improves the loading in palladium. What we found is that there is a correlation between the loading ratio and the preparation procedure of the material. We started from the same piece of palladium, then we cold worked it to reducing the thickness to different thickness, 100 microns, 150, 450 microns, so with different reduction rates. Then we annealed the samples to different temperature, and we found that there is a maximum. What does it mean? That then we perform a scanning electron microscope analysis, and we correlate the grain size to the thermal treatment temperature. So there is a maximum loading ratio with respect to the grain size. We have found that the grain size is a significant parameter to understand, to improve the loading ratio, then the probability to have a successful experiment of heat excess. The best range of grain size is in between 50 and 60 microns. This led us to obtain in very high reproducible way, high loading ratio, I mean over 0.9 D on PD. What we did then was to move to thin films, and we started to investigate palladium thin films between 1 and 2,000 angstrom to test if low dimension can help in the stress relief. We coated a nickel plate with palladium by thermal evaporation, and we saw that the deuterium can more easily inside the lattice or nickel if it's coated with palladium film, with a palladium film. So this is the effect of deuterium loading. What we found is that the loading is higher in case of PD film on nickel with respect to nickel bulk. This is just a preliminary result, but we saw that this improved quite a lot the reproducibility of ICCF experiment.
Thank you. Thank you very much for finishing well on time. Our next speaker will be Dr. Isobe. He is once again a young colleague of Dr. Takahashi from Osaka University. I guess we have to appreciate the efforts of Dr. Takahashi in bringing so many young people to this aging audience. Special appreciation prize.
My name is Yuji Sobe from Osaka University, Japan. We carried out simultaneous measurements of neutron, X-ray phase heat, dewatering ratio using open diesel type electrolysis system. This is schematic diagram of measurement system. Two X-ray detectors and two neutron detectors were used for nuclear product measurements. As we use two detector system, the reliability of the measurement data was improved by seeing constantly happening events for two detectors. For example, if one of the detectors detected an increase of signals and the other detector did not detect the signals, we considered it was a noise or statistical fluctuation. Heat production in cell was measured by the mass flow calorimetry method. Temperature of the cooling water was measured with platinum resistant temperature device and different thermometers at entrance points and exit points. This is the arrangement of the nuclear product detectors. 213 neutron detectors and two cadmium telluride X-ray detectors were set up near to the cell. The X-ray detectors were inserted into the holes made from the bottom wall of the cell in order to make the distance between the cathode and the detectors as short as possible. This is the structure of the electrolysis cell. The electrolyte was lithium oil. And coolant pipe was set in cell and heat produced in cell was removed efficiently. PD cathode was set at the electrode holder. The temperature of the electrolyte was monitored by using this RTD. Degree of loading ratio was obtained by measuring the electrical resistance of the cathode with mirror meter and comparing it with the non-calibration data. This is typical data of calorimetry and loading ratio obtained by using this system. The current mode was a step-up mode. This green line is input power. Red line is output. And This blue line is the overfeed. The broken line means the estimated error around 3 sigma value, about 3.3 watts. This nuclear product data was obtained in the same run. Upper broken line is 3 sigma level estimated by using Qiao calibration run, and lower broken line is average. We could complete a system which made it possible to measure reliable nuclear data and excess heat production and loading ratio simultaneously. And we expected various experiments with different conditions after this conference. More details on the system. As a result, the reason for planning experiments are shown in our poster session. So, if you have some questions or comments about this work, please let me know. Thank you.
Thank you very much for being completing on time. Our next speaker is Professor Li. He will be presenting the paper on behalf of his colleague, Dr. Qiao from China. Some of you may not know that Professor Li also takes a very active part in the hot fusion program in China. So we don't know how he juggled between hot and cold fusion.
Thank you, Chairman. I'm Li. I'm presenting for Professor Qiao. It's a work for the gas loading experiment again. Yesterday we talked about excess heat in the gas loading system. The amount of excess heat is too small to be justified as non-chemical origin. So we look at the nuclear product in the deuterium plating system and hydrogen plating system. This is the helium analysis using the mass spectroscopy. The resolution of this mass spectroscopy is 700, which is greater than 156, which is necessary for to distinguishing from deuterium molecular to the helium form. In order to distinguish from the air leakage, we measure the ratio of the helium-4 to the neon-20. That's for the deuterium plus palladium. And before this experiment, we measure the standard air. This ratio is about 0.3. After this measurement, we do this standard air experiment. The ratio is about 0.3. But this number is 0.55. Then we start to measure the pure deuterium gas. The helium amount is very, very small. Then we enlarge it, and we get this ratio is still 0.3. So we are sure there are helium source inside this water. But we did this only once after 1 year. Now we go to the hydrogen deuterium hydrogen palladium system. A piece of palladium foil loaded by hydrogen is sandwiched in between two pieces of solid-state nuclear trap detector. We put them together after several months. Then we etch these two pieces of solid-state detector, and we see this kind of image. Each hole is a charged particle signal. If we look at this area, comparison with outside, very clear distinguishing. And we look at the front side and the back side, the very clear distinction. And we compare these two sides. We found one spot here, and we got two signals. The pattern is very similar. So we are sure there must be some active region on the plain foil loaded by hydrogen. We look at the zinc components also, and we look at the rare earth components also here. That's a rare earth element. And we saw its distribution on the surface of the plating wire loaded by hydrogen. I will tell you more in my poster session. Thank you.
Thank you very much. The time is taking over the mic. I request Roberto Monti. He's from Italy, but I understand he's presently in my course.
Okay, after experiments made in test and in 92, it was clear in my opinion that alchemy is an experimental science. As a consequence, following the principle of banality, through my test I used one only method, always, solve it coagula, eliminating the solvent to coagulate, together with the right fire and the favorable consolidation. Now I'm to the point to make some kind of control for industrial remediation of the radioactive. So I compared it to show another thing. That is that first, obviously, since many of you maybe remember, my test for 1995 was so astonishing that they could not be accepted by the scientific community. Consequently, I was compelled to have this test validated by an independent laboratory. So European Technology made a contract with DeNinno in National Laboratories Italy to carry out low energy transmutation programs with that project. And the industrial reactor was built in Canada, sent to Italy. The laboratory of NES had made history fundamental tests, complete calculation of starting materials, two cold tests without radioactive elements, and evaluation of the best assembly for the reactor, and so on. After that, the second report came out with these results. I pointed mainly attention to lead, silver, and thorium. Lead was reduced in the first test by 50 grams, silver increased by 91 grams, thorium reduced by about 2 grams, 88% reduction. Because I worked before for many years and was not interested in thorium, but mainly in uranium, because after that moment I was not able to work with uranium, I had not had uranium available. So I made the second test with uranium. Note the date. This test was made in June 1997. The result was lead was reduced by 111 grams, silver increased by 85 grams, and uranium reduced by 1 gram, 12% reduction. In this previous test is already present the seasonal effect because the test made in May with thorium was 18%, the test made in June was already going down by 30%, to 30%. After the results, I decided to concentrate attention on uranium and to prepare two different compositions of fusion mix, which I called FM1, FM2. Same preparation was sent to Italy, and the results of the test following the report. Lead was reduced by 64.8 grams, silver increased by 19.6 grams, and uranium was reduced by 0.26. But as we can consider the experimental error about 5%, was considered as a slightly new result. It was important for me because I could see that the laboratory can really measure the uranium. After that, I went to make the further test on March 12, which is near the end of the wrong season. And the result was the following. Lead was reduced by 23 grams, silver did not change. Uranium was reduced by 0.77, a 60% reduction. Then The 1st of April, I made a quick test just to present the results here. That was reduced by 29 grams, still did not change. Uranium was reduced by 1.46 grams, 30% reduction. You see that the beginning of the season is equal as a result as the end of the season the previous year. Conclusion, all the tests made since 92 show that the alchemy ints are always correct, proving that alchemy is an experimental science. Even the seasonal effects seem to be a correct in. This time for the test all equal, we follow the rule here, and new ints will be tested. But let's remember that the seasonal effect is not a silly thing, because in 92, the Federation project failed because we were not aware of the seasonal effect.
Thank you, Dr. Monti, for donating us 1 minute. Next speaker is Tom Hassel, the chairman of the meeting, I think, in Montreal from Belgium.
Thank you, Mr. Chairman. Start with the conclusions of the 5-minute talk. This is a search for nuclear reactor products in old cathodes, doing a little archaeology on cathodes that are sitting around for several years since they presumably produced, or allegedly produced excess heat. The conclusions I've drawn from looking at about 30 of them by a special non-destructive method, and I'll show you in a moment, is that we've observed boron-10 depletions. Boron, you know, is a normal impurity in most pure palladium. And I can see boron-10 with this method, but I cannot see boron-11. And I observed its ratio to palladium-105, one of the main isotopes of palladium, in the heat-producing palladium relative to the virgin material from which that cathode originally came. And we, of course, assume that that particular batch of palladium is the same and uniform throughout, which is not by any means yet proven. And it remains to correlate fully these depletions that I've observed with the amount of excess heat observed. Now here's the method that we're using. Very simple one in principle. Neutron beam from a research reactor. This happens to be at University of Missouri, Columbia. We place the palladium sample in the beam, and it captures thermal neutrons. And each isotope there produces gamma rays that are characteristic of it and no other isotope. And we measure it with a germanium crystal that is protected from its Compton spectra by an anti-coincident annulus of sodium iodide. Around the whole thing we have a cadmium shield to prevent the scattered neutrons in this area from interacting directly with the detector and the sodium, although still some of that occurs. Here's the spectrum of a limited region of the spectrum. Here's the boron so-called peak. Oops. Boron-10 produces an N-alpha reaction, giving you lithium-7, recoiling at a very high rate. And so it gives you Doppler broadening of its otherwise sharp peak. So I have a 20 kilovolt wide spectrum of boron-10, and here is the main peak from palladium-105, but it's coincident with the annihilation radiation at 511, and this is at 511.8. They're not resolved, so I must subtract away the annihilation radiation background, which is always present here. And here's the cadmium line, which I use to normalize these things from one to the other. And then here's the 616, 622 pair, also from palladium-105. Here's a 717 kilovolt gamma, also from palladium-105. So I have 3 or 4 ways, many others perhaps, to make this relative measurement of the area under these peaks relative to each other for the various cathodes. Now, here's some results, and I expect that you won't be able to do this here, but perhaps you can stop by my poster session and we can discuss to what extent these are logical reductions. But I point to a set that I got from Stanley Pons, which he hasn't told me yet how much heat he produced, but he did say that this was a producer of heat and this was the virgin material from which he made it. You can see it had a 9% drop in the boron-10, boron-to-palladium-105 ratio, which implies that if you are burning boron-10 here, by the say the D-alpha reaction, making helium and about 17.8 MeV per reaction, then we would see if that corresponds to what you would predict from his heat measurement. Again, he had a virgin material here for 3 2-millimeter cathodes. This is a 4-millimeter cathode. And again, we have a very remarkable 35% reduction down to 0.65 of the boron in that one, 15% there, and then barely 4% there. So we'll see if those, when I finally find the amount of heat involved, correlate with that. Kazagi of the University of Rome gave me a whole set of 13, of which 8 here are here, and Mizuno gave me a couple which did not show any major reduction. In fact, within the limits of error, probably about the same, but in general, no reduction in boron-10. However, I wouldn't call this exhaustive. By any means, it's suggestive, and I hope that some of you with heat-producing cathodes could come by and offer them to me, and we'll see if we can get them analyzed. And even in my retired state, I think I can still manage this on my own personal savings income.
The next speaker is Bill Collis from Italy.
Well, I'm going to talk about a software product which runs on a normal PC and analyzes what I like to think is the vast majority of nuclear reactions we're interested in, which are the form A plus B getting to C plus D. And there are 4 pieces of information. A simple calculation, a simple reaction you can calculate. First of all, the energy, the particle change, the spin change, and the gamma suppression factor for the separation of the 2 products. Now, of course, you could also calculate a gamma factor for the fusion of A and B, but as I don't know what the energy of that is in general, I know what the energy of the reaction is, I can't calculate that. And in addition, I can specify certain other parameters like energy transfer from the outside world, if your particular theory is interested in that. But the most important factor about this software is that it allows you to incompletely specify the A plus B makes C plus D equation. You can say that A and B may be naturally occurring isotopes, because we're using natural materials in our television experiments. We could say C is helium-4. We could say D is something which is not radioactive, because we know we don't get more radiation from the result. Unfortunately, there are over 2,600 nuclides. So the combination of A plus B to C plus D is 2,600 elevated to the 4th power, which is about 10 billion or so nuclear reactions. But surprisingly enough, even if we specify completely, there are no restrictions at all, I can scan through the whole lot of the software in a very short time indeed. So it's a perfectly practical method of searching through any number of reasonable nuclear reactions to find out every single possibility that satisfies the criteria we want to impose. Briefly, I'll show you some of the things you can do. NSAP is the name of the program, and here on this first line, we've got a proton, something natural producing a neutron, and asterisk means anything at all. And we can see how we can produce neutrons from protons in typically a light hydrogen system, where we heard that just this morning that neutrons have been measured. But that's not the purpose of my paper. I want to look at 2 rather relevant topics arisen recently. First one is the nickel hydrogen system. I will look at every single reaction which can produce energy in the nickel hydrogen system. And there are really only 3 categories. We have hydrogen fusion, which has already been covered, but there are only 3 or 4 reactions. We can look at nickel and a proton. We can look at nickel and a deuteron, which I'm not considering here, in fact, and nickel plus nickel, but there really are no alternatives. And And if we go through these, we can see that the only products, only heavy products, I should say, are iron, cobalt, nickel itself, and copper. Now, if we had to do a couple of cases of do the deuterium fusion, we could possibly produce manganese. But I would like to emphasize this does not correspond to experimental results. So we can say that whatever is causing some of the impurities which were, say, reported at the acid conference, they are not reactions which form A plus B going to C plus D. And that is a miracle. So when some rather exotic theories were presented, rather complicated ones perhaps, maybe we should give a little bit more attention. Because we're looking at something more complicated than A plus B going to C plus D. And the second example, I've got time? Okay, I've just got time, is the Marie's fission of the heavy element 310. I think this would be of particular interest to Douglas Morrison. Now, because the computer program can calculate gamma separation suppression factor, I can calculate the relative rates of all the fission products of this particular superheavy isotope. Now, you may say that I don't know the cross-sections of the reaction, I don't know the shapes of the nuclei and all this sort of thing, but if you apply the theory to, say, uranium fission, you get a very good, perfectly, reasonably good fit to the products of uranium fission. So I think we can say that this is a reasonable method to calculate the fission products of a superheavy nucleus. And we get this rather strange four-peaked curve here. And very briefly, this corresponds to lead-206, ytterbium 172, barium 138, and ruthenium 104, more or less. Most of the products are stable in contrast to what we would expect from normal fission. Now, in this particular case, I haven't included spin or parity conservation, but if you want to talk to me about that, I'll be able to host a session later on this afternoon. Thank you very much.
Next speaker is Dr. Irina Sabatimova from the Podolsky region on the low discharge experiments underway.
We studied the heat and transmutation effect at palladium, palladium alloys, and pure metals such as vanadium, zirconium, silver, the titanium, and hydrogen low discharge. We have such results for heat comparison for different materials. For example, this is heat efficiency, this is temperature, this is calibration condition when the temperature became constant. This is palladium, this is palladium nickel alloy, this is palladium ruthenium, this is palladium platinum tungsten alloy. This is for equal condition. Each picture for equal condition, for equal cathode design. This heat efficiency for palladium and molybdenum. This is for pure metal vanadium, zirconium, and silver. This is non-calibration condition when the temperature increased. This is incident angle tension, delta temperature to delta tau. This is current density. As can see in this methods, we can see two different regions for heat output. The first region with small current density and temperature, and second region for big current density and more temperature. In first region, there are two mechanisms: heat output. As you can see, in using this non-calibration method. First region, heat output, when the deuterium evacuation. Deuterium output and heat output. In this region, we have not deuterium in the big value, but we have big heat output. Main result for heat measurement. Glow discharge method is simple and abstract method for different materials composition. First, it's possible to increase the working temperature by addition of the impurity elements. It is possible to stabilize the iteration parameter, to enlarge using the lifetime without loss of the property Cathodic materials, using the impurity addition. Estimation of the heat efficiency in the dynamic emission transition show that there are two regions with different mechanism of the heat output. First region has low temperature and low current density and depends on the hydrogen loading. The second region has more different density and temperature, as does not depend on the loading.
I know you have another paper. Maybe you can summarize just 1 minute.
For isotope, for transmutation effect, we have transmutation effect always as we have heat effect. For example, this is we have reproducibility for different isotopes in different experiment. This is experiment before this different parameter of the glow discharge. We have always 105 masses and 110 constant always, practically. We have not isotope shift for palladium at hydrogen experiment. We have masses carbon and some always. Just a minute, please. This is cadmium, stannum, and other masses in the experiment. For example, palladium ruthenium, where more heat output, and palladium platinum, where output masses 164 to 177. And platinum isotope shift another. 1 second. The next transmutation result, transmutation effect exists in the Golgi chain experiment, confirmation in the deuterium and the hydrogen experiment. There is a small difference in the transmutation result when heat efficiency for the deuterium and hydrogen experiments, we know big difference. There is big difference in the transmutation result when heat efficiency difference for palladium and deuterium experiment more than 50%. Oh, that's all.
Thank you very much. Thank you. Thank you. The next speaker is Dr. Violante. He will be presenting the paper of Dr. Monti. Dr. Violante.
This is a material science paper concerning a non-destructive method to evaluate the thermal properties of palladium hydride. The starting point is this one. In our field, we are interested in have a good knowledge of the loading of palladium. But with the measurement we usually do, we can know an average value of the concentration, and we have to apply some mathematical mechanism to extrapolate the possible profiling cycle. Then the idea is to try to evaluate how the thermal properties of the palladium hydride change when the concentration of the hydrogen or the helium increases. Usually, we know that in diffusive media, we don't have wave behaviors unless we produce such a behavior with a pulsed source. This is quite similar to what we are doing when applying low high current states in doing electrolysis. So the concentration profile after the first perturbation, the concentration profile is something like that. Then when we switch off the signal, the concentration profile moves in this way. And then if we switch on again the source, the concentration profile is something like this. So we can approximate such a behavior to a wave. So in few words, we have a DC signal with the lowering impulse of the AC signal. And it's the AC signal that will be treated like a wave. And the AC signal disappears when the distance from the source is larger than the diffusive distance in the medium. So the basis of this concept that mathematically can be observed this way. If you consider oscillating the AC function and you put this one in the heat transfer equation, it translates in the Helmholtz equation of the waves. But there is a wide literature on this. So if we pick with a laser beam surface of material, with this pulsed signal, we obtain oscillating components of the temperature with the proper phase that is correlated with the media, which is a function of the thermal diffusivity. Then, if we check for the amplitude and phase of the signal at different positions on the surface, we can plot the phase against the lateral offset. And the slope of this line is correlated with the diffusive length, which is function of thermal diffusivity. So by doing some simple calculation, we can evaluate the thermal diffusivity of the media, and this value are reported for a sample of palladium that is treated at 900 centigrade or not. Well, by applying the technique to loaded and unloaded samples, we obtained such a value for thermal diffusivity. So the thermal diffusivity decreases to about 20% in loaded material. And this is a very important point because we know that the material changes properties from a metal to an anhydride. It's right, it's right so. With some little more complicated mathematical approach, we can study this effect for an homogeneous media, obtaining such a profile of the thermal diffusivity inside. And this profile is obviously correlated with the concentration profile, indicative in like this. So for more details, we are posted.
Thank you, Dr. Evan. We now have Dr. Scott Qiao from Arlington, Virginia.
The title of my poster is Periodic Order, Symmetry, and Coherence in Cold Fusion. It's sort of a partner poster to the one I presented yesterday titled Really Cold Fusion. It's work I've done with Qiao. And the poster has 5 parts to it, as you can see: introduction, importance of symmetry, periodic order is a special form of symmetry, lattice-induced coherence and periodic order, coherence and lattice-induced nuclear chemistry. I'm really just going to touch upon this, and this. Solids at room temperature are periodically ordered. High-temperature plasmas, HCPs, are disordered. Because solids have periodic order, they can coherently absorb momentum all at once at a point, discontinuously, and through recoil processes in which the solid as a whole moves in response to a collision in an isolated location. As a result, in ordered solids, very often initial momentum of colliding particles is not conserved by particles during collision. This is an idea that fundamental in solid-state physics that Schwinger touched upon early on in his discussions of cold fusion. At low intermediate temperatures, these kinds of collisions dominate following important effects: the conduction of heat and electricity from a standard textbook, the fraction of the neutrons, electrons, and X-rays, again from a standard textbook, and the Mossbauer effect, which was the way Schwinger talked about it. Because the idealized limit of stoichiometric palladium deuteride is periodically ordered, there's reason to believe that further deloading will result in the occupation of ion band states by the nuclei. It's also probable that potential nuclear reactions and transport of ion band state D will be dominated by these kinds of non-momentum conserving interactions, especially at low temperature. Because these non-momentum conserving processes involve indistinguishable particles, as in the case of D, and occur completely elastically, distinctly quantum mechanical forms of coherent interaction become possible, in which periodic order is preserved. Through these interactions, it can become virtually impossible to identify both the location of the interaction and the participating entities involved in the resulting release of energy. We've of course discussed this ad nauseum, really. I hope people are paying attention. Okay, periodic order is a special form of symmetry. In solids, periodic order provides a special form of symmetry that is known to have significant impact on the transfer of charge and heat, and as noted intermediate temperatures. An important reason for this is that in the presence of periodic order, electrons occupy band states, and these states share a common degeneracy with respect to changes that do not alter the underlying periodic order of the ground state. When H and D are allowed to occupy ion band states, they share this degeneracy with each other, and their interaction with each other and with the outside world must be treated using degenerate perturbation theory. The resulting description leads to a form of coherence that is distinctly non-mechanical. Lattice-induced coherence in periodic order. Important points are the following. Horizontal transitions, which are defined by a condition in which an energy and it changes by a wave vector, or h bar times this is momentum. It changes by a reciprocal lattice vector, or h bar times g is the momentum. These are called horizontal transitions. Provide a coherent form of couplings in which perturbations can be amplified. These coherent effects are the result of degeneracy and constructive phase interference. These horizontal transitions are distinctively different than the kinds of things that Peter Hagelstein talks about, for example, which are more vertical transitions. When a perturbation delta V does not exceed the minimal excitation energy of any of the band state particles, the degenerate state perturbative scheme to which this becomes important, that's what the outline above refers to, becomes rigorous. The coherent behavior that is responsible for the amplification of the perturbation occurs as a result of periodic order and degeneracy. Thank you.
The next paper is that of Dr. Kojima. Since Dr. Kojima is there, his colleague Dr. Yamamoto will give a very brief introduction to the paper, just a couple of minutes or so. Dr. Yamamoto.
My name is Hiroshi Yamamoto, not Professor Kojima, actually a friend of Mr. Professor Kojima. And he was supposed to come over and to present his technical paper, trapped neutron for the fusion model, but due to his urgent assignment, he couldn't make a travel, and I was asked to convey his best regards to your people, and also to put his technical paper on the board. Honestly speaking, I'm a mechanical engineer working for Yamamoto, but Yamamoto has nothing to do with cold diffusion. But my peculiar interest in cold diffusion forced me come over on my own expense, and honestly speaking, I'm not so much familiar with physics, and I cannot distinguish the difference between the trapped neutron and hybrids by Dr. Riffa, or DeNinno by Dr. Randy Mills, but I'm a little bit in favor of Dr. Randy Mills' DeNinno, but anyway, I hope I can convey your comment to Professor Kojima, and please come over to my Dr. Kojima's poster session, and I'm waiting for you. Thank you very much for your kind attention.
Thank you, Dr. Yamamoto. We now invite Dr. Melvin Miles. He will be speaking on, I think, the radiation measurements at China Lake, real artifacts. Am I right? Dr. Miles.
Okay, just mentioned, my name is Mo Miles from Cali, California. This is some work we did a couple years ago. We never published it because we weren't sure what the right answer was, real or is an artifact. And when we present the evidence, you can make up your own mind. Due to safety concerns, we had to have a Geiger-Müller counterbar experiments to measure radiation. Under normal conditions, for month after month, often it was within plus or minus 3 sigma, around 32,000 counts per every 12 hours. That was the usual situation. But in some cases, we saw things abnormal, particularly when we did co-deposition, that is, we deposit palladium out of solution at the same time it's being loaded by deuterium. It was normal right here. We turn the current on right here, and within 12 hours, the first count after we turn on the current, the radiation count is up to here, which is a 73 sigma effect. It would continue for a few days, and often then it would fall away and go back to normal. But we thought that was quite unusual. There's some problems with it, however. We couldn't reproduce it that well. Another Navy laboratory came with germanium detectors and X-ray detectors to put into our experiments, and we tried to run many experiments quickly while they were there, and we saw no effect. In fact, we had even lower than normal because of the screening blocking by the other detectors that were present, but we could not reproduce the effect while they were there. Well, long after this, I finally figured out probably what the reason is. You involve chlorine, and if you don't allow time for the chlorine to dissipate or don't flush it out, then you don't get this anomalous effect. Chlorine has some effect, I don't know what, maybe passivates the electrode or whatever, but if we did the experiment rapidly and didn't allow time for the chlorine to get cleared out, our success rate was 0 out of 11. That was when this the laboratory brought this equipment in, basically. When we flushed out the system with nitrogen, we saw this 5 times out of 8. Or if we didn't rush the experiments and took our time and set another experiment up 3 or 4 days later, then we got this effect 3 out of 5 times. So it seems like it is definitely related to chlorine being in the system when we start the reaction. This is another example where we had normal counts, we turn on the current, and then we got a large peak right here of radiation counts. So you can come by the poster. We have other examples with other detectors, also sodium iodide detectors. If we had a solid electrode, we would see this effect also, but it took maybe 1 or 2 weeks before the radiation would show up. Co-deposition would appear almost immediately within the first 12 hours. But with a solid rod where it takes longer to load, it would often take 1 or 2 weeks before the effect would show up. Okay, if it's an artifact, the reasons for that is never reproducible. And sometimes, many times when we tried these other detectors, one detector would see the effect, other detectors would not. So if anybody has an answer to that, I would like to talk with him. The reasons why we think it's real is observed by other methods, X-ray film exposure. Several different detectors showed similar effects. Also, sodium iodide detectors showed an effect. The co-deposition experiments, the effect showed up within a few hours. Solid rods, it took 1 or 2 weeks. How could this just be a coincidence? That's my question, because we know it takes a rod longer to load. We move the detectors away, and the radiation would drop off. The radiation would track back to the cells. You switched on battery power, the radiation was still there. It didn't matter whether that had plugged in on battery power. And we never saw anything unusual when the experiments were off. Okay, thank you.
Next have Dr. Akbar, and I think the paper will be presented by Dr. Kasagi. So on ion from carbon and oxygen and the electron discharge.
The report of my transmutation experiment. Hello everyone. I am a member of a new alchemist club, and I was accompanied with 10 members here. We have the workshop 3 or 4 times per month, and over 500 people have already experienced transmutation. You can try easily and enjoy our experiment on the kitchen table at home. It takes only 5 minutes, which is as short as the time allotted for my speech today. I'm happy to present to you all that anyone can challenge this low-cost, wonderful experiment only with our pocket money. Please take a look at my posters and handouts for the details. I believe vegetables are great alchemists. When I will travel, that perhaps the income does not meet the expenses in my practice of organic calculation. I read the book written by Dr. Louis Kelbrand of French Academy, titled Transmutation Biologique et Naturelle. Reading through this book, I confirm that atomic transmutation took place at natural temperatures and pressures under right gravity. Photo 1. Photo 1. CaO plus MgO yields KNO3 is potassium nitrate. The following formulas is well-known cycle using simple arithmetic. One example here. Several years later, I carried out the experiment according to the report of carbon arcing discharge by Mr. George Osawa, founder of Nippon CI Association. And the result was that magnetic reaction powders were produced only in 5 minutes. Photo 2. Photo 2 shows the path map of magnetic reaction. Photo 3 shows the picture of the pretty shining powder in microscope. Discharge conditions for general use, 45 volts and 30 amps or more is recommended, and for industrial use, 80 volts with 100 amps or more is desirable. In this case, it takes 20 seconds only. The materials for electrodes are all 3,9 pure and having been analyzed by EDX again beforehand. Diagram 1 shows low carbon. Diagram 2 shows carbon discharge. Diagram 3 and 4 indicate the X-ray analyzed value. Reproducibility of this experiment is almost 100%. All the participants in our experiment, schoolboys, housewives, and bankrupts, who have only a little knowledge of science. Our goal and prospect. People in the world are around that the natural resources which will be used up only in 20 years or so. Now we do hope to develop this transmutation technology, which is a breakthrough of modern science by clean energy. In ICCF's pioneer spirits, for the Mother Gaia and the happy life and the human dreams, I would like to greatly appreciate Dr. Fleischmann and Dr. Pons, who kindly introduced us to this conference. And I want to send many thanks to all the pioneers of ICCF who made this meeting so active with the great effort of many years, and who gave us this wonderful opportunity of the presentation time here. I would like to send you all my best wishes for your health and success. Thank you.
Friends, just one moment please. I have to say we have two more speakers, Dr. Natoya, who was missed earlier, and one more. Kindly bear with us, and we'll try to wind up in another 9 or 10 minutes. So I call upon Dr. Rico Natoya. Natoya, please. Dr. Natoya from Hokkaido University, Sapporo, Japan. And after her, we have one last speaker from China. Please bear with us.
In recent 6 years, we have reported on some evidence for the low temperature nuclear reactions. Our experiments have been related mainly the observation of heat evolution and gamma spectra during electrolysis and analysis of tritium and other non-radioactive species after electrolysis by use of alkali metallic ion solutions of light water and as cathode porous nickel or platinized platinum. Then, as product of nuclear reactions, these species have been found in the cell. I'm sorry. Yes, okay. Yes, okay.
Would you raise it?
Moreover, you can see, we have found that positron annihilation was occurring. Today, I want to speak about the result in the same experiment, but the data become more and more accurate and reproducible. In this report, our interest will be focused on gamma spectra of platinum derivatives. Peaks due to platinum derivatives often appear even in a cell like nickel cathode, because always we use platinum wire as a hook or cathode and as an anode. You can see here several peaks. They were identified by platinum derivatives. One day's experiments were repeated more than 10 times. This figure is exemplified from there. Comparing with the background, the appearance of potassium 43 two peaks and the peak at 2.22 mega electron volt due to new NP reaction, such as okay, maybe. Thank you.
Thank you, Dr. Vijaya. We have the last speaker for this afternoon, Dr. Lu from China. Will you kindly introduce yourself and your organization?
I'm Monti from China Army of Engineering Physics. My paper is on an experimental study of the anomalous nuclear reaction in the palladium deuterium systems. In my paper, an experimental study of the palladium deuterium system undergoing temperature cycling was done, and the results were presented. Experiment. First, materials. In our experiment, palladium plated diatomite and then sodium liquefied zirconium cobalt and the zirconium vanadium iron oils, which used as experimental materials. Experiment procedure. This experimental materials were first put into a high-pressure container respectively. Then they were discussed and saturated with 5 to 10 MPa deuterium gas at liquid nitrogen temperature. Then the container was undergoing temperature cycling between room temperature and the nitrogen temperature. Then the deuterium gas was released from the container and to detect the reaction reactant. Third, tritium and helium measurement. After temperature cycling of these containers, a small buster was used to oxidize deuterium gas, which from the containers into heavy water to measure tritium concentration in the samples. Then the container was heated to about 850 degrees centigrade to collect helium samples. Original deuterium gas was also oxidized into what as a tritium background to create tritium in original gas. So let's see the experiment results. Tritium concentration in the water samples were tested using LB+1 scintillation counters. Atom ratio of helium-3 over helium-4 in helium samples were also analyzed using MM3000 mass spectrometer. The results were listed in Table 1 through Table 5. As shown in Table 1, only in the palladium deuterium system, both tritium concentration and atom ratio of helium-3 over helium-4 was greater than the background. Table 2 is a repeated experimental results using palladium plated diatomite. So, from this table, all of the samples except number 3 have tritium anomalous. Table 3 is a comparable experimental results using hydrogen and deuterium gas. From this table, we can see both hydrogen palladium system and deuterium palladium systems. They exist tritium anomalous. using no background tritium deuterium. I'm very glad to have a detailed discussion after this lecture about maybe some tritium contamination, tritium and helium movement. So this is conclusion.
All right, thank you, John.
In the palladium diatomite deuterium system, ambient temperature cycling, our experiment results have shown that there exists alumina tritium which is 1 to 2 orders of magnitude greater than background. The results suggest that nuclear reaction between
try to tell you tonight how to extract helium if you're doing cold fusion experiments, how to measure helium. The format will be a little bit different than last night. We're going to go through sort of an organized program first, and then we'll have a question period at the end because we have several different topics. I'll give an introduction. My name is Mel Miles from Qiao, California. I'll have a brief introduction, then Ben Bush will talk about the actual extracting helium and how to measure helium. He's done experimental work in this area. In fact, he's the one that got me started on helium and offered to do helium measurements when he was at the University of Texas. And the first helium measurements we did, I collected samples from China Lake and sent them to University of Texas, where Ben Bush, with the help of the mass spectroscopists there at University of Texas, did the first helium measurements. Later, we used commercial laboratories, and some of you may know places you can have helium analysis done. The one that we used in Amarillo, Texas, is now the business, I understand, Department of Interior. But there are other places, like Brian Oliver, is still doing measurements. But anyway, after my introduction, Ben will go ahead and take some of the time talking about how to extract helium, how to measure helium. Then there's a special part of the program. Dr. Cathodic is going to speak on the hollow plating cathode work of Dr. Arata in Japan. He's done a lot of studies of his work, and that involves helium measurements as well, and so we'll address that topic, especially how it relates to the helium measurements that were done there. To get started, I wanted to show one view graph before I turn over to Ben Bush. This summarizes the major problem with helium analysis if you're doing electrolysis. This first column shows the excess power that suppose you measure and how much helium you would expect in your gas sample you collect if we assume it's the DD fusion going to helium-4 and 23.8 MeV. Also using 500 milliamps, which is very typical current that we use in these studies. It varies a little bit if you use a different current. Higher current will dilute it somewhat, lower current will make it a little more concentrated. This shows the percent error, assuming the error is plus or minus 1 part per billion. That's the error of the Amarillo lab, the Department of Interior lab that we used in Amarillo, Texas. The error was about plus or minus 1 part per billion. And this is the calorimetric error. Assuming for my calorimetry, it's about plus or minus 20 milliwatts. And so for 100 milliwatts of excess power, you would expect about 11.2 parts per billion of excess helium in your sample. And the error on that measure would be about 8.9%. The calorimetric error would be about 20%. And then this shows the same things for 200 milliamps. 200 milliwatts, most of my experiments have been somewhere in between 100 and 500 milliwatts. I've never seen excess power in my experiments larger than 500 milliwatts. So at 500 milliwatts, you could expect 56 parts per billion helium. Your percent error is going to be 1.8%, and calorimetric error would be 4%. I drew a line here because this is very difficult to get to these other excess powers like 1 watt. Or if you wanted to reach the concentration air, just equal the concentration air, that there is a helium-4 in air in the atmosphere, you'd have to have 46.6 watts of excess power. And nobody that I know doing electrolysis is ever come close to that. So people that say, we'll believe you if you can get more helium than in the atmosphere, it's almost impossible because before I get even to 10 watts, and all the calorimetric systems I've used, it would boil away. So you would not even be able to get to that point, equaling the concentration in air. So you have to really work on controls, experiments to show no excess power, and see what your background helium is in that case, and compare with cases where you have excess power. And I just put a footnote here. I don't know how many people took note of this when it was published, but Nate Lewis of Caltech and Al Bagley of MIT, they reported they found no helium. Well, of course, first they said they had no excess heat, so they shouldn't have expected any helium. But even if they had excess heat, their detection limit was 1,000 parts per billion. So they would not have been able to detect any of these things unless they got up to at least 10 watts of excess power. They would have needed 10 watts of excess power just to reach their detection limit. And yet a lot of people think that was proof that there was no helium in their samples. People don't realize what a detection limit they were using in that case. But you have to do measurements in the part per billion range, as you see from this graph. And that's the point I wanted to make. Now turn the time over to Ben, and he'll tell you how to collect samples and do measurements in this range of helium 4.
Helium analysis, you can do several different things. You can do analysis of the cathode. You can do analysis of the electrolysis off gas. And you can do that in 2 different ways. You can do it in the long term, allowing the helium to build up, or you can do it in real time. You can do the helium analysis of the cathode, and incidentally, Maury and a bunch of other people with the big study did that back in 1990. You can do that by wrapping a bit of aluminum foil around a piece of palladium. You cut off with a knife. You need to use a new knife blade because you don't want to transfer helium-bearing palladium to your piece you're cutting from earlier cuts. So anyway, you wrap that piece of palladium in aluminum foil and then put it in your mass spec system and heat it. And the aluminum foil will alloy exothermically with the palladium, thus melting it. And since you melted the metal, you've released the helium into the mass spec. Now I did this, for example, with some contemplation, cathode materials versus a piece of virgin palladium from the same lot as the cathodes were made. That was the virgin piece, and here's the 3 cathodes. And I would call that no helium found, and the helium-3, helium-4 isotope ratios were about that error. So what I'm saying is you're not going to find helium if you look in the cathodes, and that's what Maury found way back when. Back in 1990, no helium in the metal. So this is not really a surprise because the electrolysis delivers its energy to the surface of the cathode. So I would expect the reaction to occur at the surface. Just thinking about it, I would. You've got something like a 10 to the 7 volt per centimeter drop at the cathode surface. There's a lot of driving force there, if you will. So my conclusion is that I kind of expect cathode analysis of the metal to be sort of useless, but don't take that as too strong a statement because it's not quite that simple. Okay, electrolysis off-gas sampling is where you want to look if you think it's a surface reaction. And there's 2 ways to do it. There's long time and real time. In the long time, you seal up your system and you allow the helium to build up. It sounds real good because you can get more helium concentration than is in the atmosphere. That's the idea. Well, it sounds better than it is because the air contains a lot of helium. It contains 5.2 parts per million just outside. In laboratories, a lot of times a bit higher than that. Helium diffuses through glass and plastics at significant rates in the long term. And so you have to take that into account. So you need to make an all-metal apparatus, and for example, that means you have to have all-metal valves. You use Kazagi VCRs or copper gaskets. You use expensive Nupro SS4 valves, all-metal gaskets to fit the system together. And your gas sampling equipment has to be, again, all metal. You have to flush this equipment out. Electrical feed-throughs need to be high vacuum type, insulator sealed, incorporated type stuff. They're like spark plugs. They're ceramic electrical feed-throughs. They're quite small, and they will keep the helium out too. You can play tricks, like you can put your calorimeter and gas system underwater and bubble nitrogen through the water to get rid of the helium in the air, because there is no air in there. You've sparged it out. But you've got problems inside the calorimeter because you've got corrosion, so you've got to put in glass sleeves or plastic sleeves, and they'll entrain helium, bring it into the system, and it'll diffuse out into the system. Hopefully that would be a small problem. The system has to remain sealed, and this is the big problem. It has to remain sealed over thousands of hours continuously. One mistake, you've got to flush it out and start all over again. And the system's an explosion hazard, because if the recombiner wets, it's going to build up pressure. And when it does that, you've got a bomb building itself up. In my view, it's kind of an untenable way to approach the analysis. You do the real-time analysis. This is the method that we found to work. You can get many more samples, and it's got some real advantages in that the system is self-flushing. So what I'm saying is, you've got the calorimeter with the electrolysis cell, and the gas is flowing out through a bubbler all the time. So it's flushing the system out all the time. Every system volume of gas that flows through the system takes out half the contamination that was there originally. So it's cleaning itself up. It's using glass and taking a bit of care, taking on VCR fittings, metal fittings, wherever I can, taking care. I can easily get down into the parts per trillion range. Now, air contains parts per million, supposedly going to measure in the parts per billion range. 100 parts per trillion. I've gotten to that many times. It's pretty straightforward to do because the system is self-flushing. This is the system Anomalously and I always use. It's a self-flushing system. Sample flasks, you have to store the samples. You're going to have them analyzed. You have to process them and so on. Sample flasks need to be all metal. Again, you don't want helium diffusing in the air. And to clean up the flasks, you need to bake them out at about 100 degrees C under a good vacuum, say 10 microns vacuum, over a period of 4 hours, and you flush them repeatedly with liquid nitrogen boil off gas. Liquid nitrogen is self-sparking. As the gas boils away, it flushes out the helium. It sparks it out. You want to use, again, Kazagi VCRs, metal fittings, wherever you can. And you're going to have to take into account the volume of the sampling flask and the electrolysis current in your calculations of how much helium you have for how much heat you're developing, how much energy you're generating in the system. And you got to watch out in your calorimetry for unwanted recombination, because it, of course, creates an apparent calorimetric error unless you measure the amount of recombination that's there. Usually it's not a problem. Usually you don't have any recombination. If you're going to do a helium analysis, you're going to do mass spec. That's the way you're going to do it. That's the method that exists. That means you got to remove the deuterium. You got to get it out. Deuterium has a mass of 4 and it's going to mass for helium 4. HD, molecular HD, has a mass of 3. It's going to mass helium 3. Now, the mass spectrometers are made of steel and hydrogen, which is absorbed absorbed into the steel. So now you've got a situation where if you contaminate a $500 million mass spec with deuterium, there's a lot of proton in that metal. Also, you're going to have an HD source. So you permanently blinded a $500 million instrument to the thing they're really interested in, which is helium-3. So they won't let you do it. So I just say no. Okay? But you don't have to make it that hard. You can do a qualitative mass spec just with generic mass spec. This is what I did at University of Texas originally. We just took the mass spec that was there and used it. What I developed was two-stage activated charcoal cryofilter. The first stage sort of sucked the sample in. It was liquid nitrogen-cooled activated charcoal. It sucked the sample into the filter system, and then I opened it to filter it, cleaned it up further. The mass spec, the baseline separated the D2 and helium-4 peaks, and so we could do the analysis, but it was qualitative that I couldn't quantitate accurately the amount of helium I was looking at, there's gas dynamics, soil, and so on. It's a bit of a problem. Helium-3 analysis just isn't going to be possible under normal circumstances with this kind of, generic mass spec. You can try and calibrate it, but it's going to be tough. Now, the original analysis, and here's the reference, the original analysis, what we did was qualitatively, 8 times when Mel had excess heat, I found helium. And 6 times when there was no excess heat, 6 controls, I found million above the threshold, whatever that was in the mass spec. So that's qualitative work. And the odds of getting, it was 14 experiments, that was all it was. The odds of flipping a coin 14 times and calling heads or tails every time, getting it correctly, is 1/2 to the 14 power, 0.0061%. So it was no accident. Well, you want to do a quantitative helium analysis. That means you're going to use a fancy mass spec. You're going to be talking with people who do helium-3 analysis for a living. That means you're going to get rid of the deuterium. The way you get rid of the deuterium is you burn it up. There's a copper oxide column heated to 450 degrees C, where thereabouts. Then the deuterium is now D2O. You trap the D2O with liquid nitrogen traps. So you take your sample into the gas system, burn it up, get D2O, trap that out, and store what remains in the metal flask. Again, all metal system, all metal system, gauge-on VCRs, metal valves, everything's metal as best you can do it. It's a high-vacuum system. Again, parts per trillion rate, helium analysis. Routine, it's just routine. And it's interesting because the helium mass spec people had no doubt that we could do this routinely. It was a foreign idea that it couldn't be done because they do it all the time. Isotope ratio analysis will help you identify the source of the helium. Air has a specific isotope ratio. And anyway, the quantitation of the helium requires the sample volumes be kept track of, and the electrolysis current, you have to account for that. Then you can do analyses of energy versus how much helium you're seeing, another D equals MC squared related stuff. And with that, I'll turn it over to Calvin. So I'll be coming back later to tell you about what you can do and what we've done with the helium analysis beyond that. In other words, what kind of interesting science you can do with the helium analysis. Calvin?
Well, I'm going to be talking about Arada Zhang's work, and I don't pretend to be a real expert in mass spectroscopy, but I have studied the Arada Zhang papers, and I have visited their laboratory. And first I would like to show you Yes. Yes. This is Dr. Arata and Dr. Zahn, and the three of their colleagues in Dr. Arata's little conference room and is associated with his office in Arata Hall, which is a building at the Osaka University that's named for him. And he, beginning in something like 91, started working with palladium powder in a configuration inside a palladium bottle, which he calls a double structure cathode. Double structure meaning the outer bottle is actually the cathode, and then deuterium diffuses into the interior, so it's a double structure. Basically, the heat measurements, I'm just going to show you one heat measurement. Rod and Zahn do their calorimetry over in this area where they have a constant temperature bath, constant displacement pumps. They're set up to study cells at one time. The cells are in dewars here. They redundantly measure the temperature of the water that's flowing into these dewars, into a loop inside the dewars and coming out, and calculate the heat from the normal mass flow relationship. So that's in one